So, we're talking about the membrane potential of a neuron and how this membrane potential can change over time from resting potential to an action potential and then back to resting. So, when we look at a graph that shows this over time, we see that the change in charge changes over time. And notice that the time is in milliseconds. So, this is really rapid change. So here we have a stimulus that causes the change in the membrane potential to hit the threshold. So this threshold potential is really important because if the stimulus is not strong enough, then no action potential will be generated. So this threshold is hit, and then the resting potential becomes depolarized. When we ask why is it called depolarization, you remember polar opposites would be like very different, right? So a -70 is very polar. The inside is negative compared to the outside. So moving towards zero in this particular instance would be depolarization, and then it overshoots zero and goes to a +30. So going back down to a -70 is going towards zero. So that is repolarization. It goes down below zero, and it even goes into what is referred to as hyperpolarization, where it is even more negative than the resting potential. So we're going to write down this process of depolarization, repolarization, and the importance of the threshold in activating an action potential. Okay. So the first step is depolarization. So this is where we're going from a -70 millivolts towards zero, and then we go to 30 millivolts. This is due to sodium ion channels open. Now, sodium is normally much more concentrated outside the cell, and so when they open, sodium floods in and it brings its positive charge with it. So sodium ions move in. Okay, repolarization is where we have +30 millivolts. We're going to go back down to -70, maybe even below. And this has to do with a different ion channel. So sodium ion channels close, but potassium ion channels open. So potassium is a K. So these channels open, and potassium moves out. So it carries that positive charge with it as it moves out. So the negative charge is stuck. It's a negatively charged molecules that are stuck inside of the neuron. So this moving, this entering and exiting of the positive charge is what actually causes the change in the membrane potential. So let's look at this diagram right here, and let's talk about this threshold. So it's really important to realize that action potentials are all or none. So I'm going to abbreviate it as AP, are all or none. So what that means is there's not a strong action potential where it goes like to +70. No, it always just goes to +30. So they're all the same. Now, if we have an increase in the intensity, it has to do with the increase in the number of action potentials generated. Not that it is a stronger action potential. So if we're talking about the sound, a soft sound generates fewer action potentials than a loud sound, or a mild taste or odor generates fewer action potentials than a strong odor. It's not that the action potential is stronger, it just produces more action potentials. So we have the threshold potential. And this is, as you can see from the graph, a negative 55 millivolts. So this is what has to be reached. So the stimulus has to be strong enough to reach the threshold. So if the stimulus is strong enough to reach the threshold, an action potential will be generated. Okay, so that threshold potential is right here, and that is the dotted line. So let's show it right here. So if the stimulus is too weak, and some of the stimuli we don't actually perceive, and so it could just generate maybe just a little blip, a little change in the membrane potential, but it doesn't reach that threshold, so an action potential is not generated. Now you'll notice that it sometimes we have this hyperpolarization where potassium leaves at a really high rate, and it actually makes the inside of the membrane hyperpolarized. So hyperpolarized is below negative 70 millivolts. So I'll just write that right here. So hyperpolarization, that's means that it's greater polarization. That means that the membrane potential is greater than, is less than, sorry, because we're talking about a negative number, less than negative 70 millivolts. So it's a negative value. Okay, so it'd be like, in this particular instance, maybe negative, what would it be? Probably 85 millivolts would be hyperpolarization.